So we will start with a presentation called Mass Balance Determination of Total PFAS and Sampling Strategies. And the speakers are JulieLions and Thomas Oudega.
So thank you, Stefan. So first, I want to thank Marco Falconi to invite us to present this session today at REMTECH Europe, and the convener are Stefan Colombano and Eric Bonnet-Bush. So I'm going to present these results. So I replace Anne Togola from BRGM, and I will present this with Thomas Oudega from Vienna. So today, sorry, yes, the issue is the mouse. Okay, so this presentation will address one of the challenges from the project, how to enhance the ability to detect and monitor IPMT. In the project, we have developed different analytical methods to detect and quantify the PFAS and some industrial persistent and mobile compounds in water, but also in complex matrices. Complex matrices are for us wastewater, soil, sediments, and also sewage sludge. To date, we have published several reports to present the standard operating procedures for different quantitative methods to quantify up to 57 compounds for PFAS, and 4 methods for the IPMTs, up to 84 compounds. We will also publish soon a report on the implementation of global methods for PFAS, AOF, EOF, TOF, and TOP, and I will develop this more on the following slides. And just to let you know, in the project, all these methods are applied in the different case studies we have with the different partners. In this project, we have 4 different labs involved conducting these analytical methods. First, an overview of the different methods we have and how they're complementary. First of all, we need to be able to quantify the total fluoride, integrating organic fluoride and inorganic fluoride. This is conducted using the combustion ion chromatography, and this is very useful to establish the mass balance, for example, during the remediation tests. After inorganic fluoride removal, we are able to quantify the total organic fluoride. If we have different preparation for the samples on solid on liquid, we are able to quantify the extractable organic fluoride and the absorbable fluoride. So this is a sub-fraction of the organic fluoride. This is our global and semi-global methods. Then we have also the LCHRMS, also named as non-target screening. And this is very useful to identify transformation products and new compounds of interest. Then if we go down, we have the targeted analysis on a selected number of compounds. For this, we have 2 kinds of equipment, the GSA and the LC-MS. Here, these methods are useful for the regulatory monitoring, but also to address the patent transport methods, and of course the remediation efficiency. This target analysis can be done on samples, directly on samples, but also after preparation. That is the top assay, and I will develop this more in the next slide. Okay, so the top assay, what is it? In fact, in this approach, we can take this sample and apply an oxidation of this sample. This oxidation will break the compounds, the PFAS compounds we can have. Sometimes it's compounds that we are not able to analyze because we don't have the target analysis and we don't know which compound is it. So this can break this PFAS in terminal products, in other PFAS short-term. Then we simplified the matrix, and then we can, using targeted analysis, more regular methods, we can quantify these terminal products. And you can see on this slide, on the top part, on the left, you have a targeted analysis with 56 PFAS, where we can see that we have different type of PFAS. And after the top assay, we have simplified the matrix, and then we have reduced the number of groups. We just have now 2 groups and many PFCA. Then with targeted analysis focusing on this PFCA, we are able to have this picture of the contents, the semi-global contents of PFAS. But for some samples, for some compounds, we are not able to oxidize these compounds. Then on the bottom of the screen, you can see that after top assay, we are not able to oxidize all the compounds. Then we can underestimate using this approach. So it can be a good tool to simplify this PFAS signal, but we have no information on the PFAS pattern. I mean, the nature and the specificity of each PFAS present in the sample. And it's also useful to monitor some matrices to make long-term monitoring, but at the starting point, we need a good characterization of the PFAS pattern to be sure that top assay is suitable with the PFAS present in the matrix and that all will be oxidized by this top assay approach. Regarding the global quantitative analysis, using this method I rapidly introduced, we are able to, using this device, to quantify what is the total fluoride, the inorganic fluoride, and also the AOF and the EOF. The AOF is for the liquid sample where we will sorb on the activated carbon the PFAS, and then we will quantify the quantity of PFAS adsorbed on the carbon. This is for the liquid sample, and for the solid sample, we will extract the PFAS using a solvent, and then we will quantify this fraction. Here, using these methods, we compare what is the information we have with the total fluoride and versus the LC-MS versus the targeted analysis. Why we are interested in this total fluoride? It's a very rapid analysis and a cost-less methods compared to LC-MS. So we have applied this TF method in a case study where we are monitoring a large-scale anti-firefighting foam plume to monitor the time of migration of this fluoride within this pilot. First, we have conducted targeted analysis. We have identified 8 main compounds, and we compare the result we have with the LC-MS and the total fluoride. And on this picture, you can see the very good correlation between the total fluoride and the LC-MS, the sum of PFAS measured by LC-MS, the 8 main compounds. So here, we have used this to monitor this experiment, to reduce the number of targeted analysis, and to have a good picture of the progression of this plume. What is the limitation of this approach? Is that we have a very higher limit of quantification for the total fluoride. As you can see, 0.5 to 1 milligram per liter, while with the targeted analysis, we can go lower. This is LOQ for complex matrices. Sorry. Okay. Okay. Regarding the AOF and the TF, we have compared what can be the information we have with adsorbable oxide fluoride versus the total fluoride. Here, we have very complex matrices, wastewater, landfill, groundwater, and we saw that the AOF is able to explain just 1 to 23% of the PFAS in these samples. There is different explanation, of course. We have some PFAS, for example, the ultra-short chain that are not absorbed under activated carbon, so we miss this fraction. The PFAS present as polymer are also not considered in the AOF, and also, for example, the structure of PFAS on suspended particulate matter or organic matter, and then they are not absorbed by the activated carbon. Then we miss a fraction. So here, our results show that we really need more experimentation to define more precisely what are the fractions we can quantify using the AOF.